In the last video, we looked at fans and how they work. These neat little machines we take for granted that are so crucial to our comfort in everyday life. And today, we'll take a deep dive into fan performance curves, a staple topic in the world of HVAC.
Every fan has what we call a performance curve, and that performance curve has a couple different aspects to it. It has a y-axis, which is typically static pressure, an x-axis, which is CFM. It's also got a couple different lines or curves in the graph area, and that's RPM, power, and sometimes you'll have system curves on these fan curves. The fan curve basically characterizes how a fan operates under different static pressure and CFM conditions. What you can tell from this fan curve with a given static pressure and CFM is how much power do I need to apply to the fan and how fast do I need to spin it. How do you create these fan curves, right? Can you use math to just create a fan curve? The answer is somewhat. You have to start with a tested set of data. So you have to develop what we call a master RPM curve first. And what I mean by that is you run a fan at a fixed RPM and you vary the static pressure on that fan by certain increments, whether it's 1/4 inch increments or 1/10 of an inch increments, whatever increments you want, and you measure your airflow and your power at each one of those points. And we develop what's called a master RPM curve from that tested data. From that master RPM curve, we can then develop the entire remaining set of that fan curve.
Today, we're out in the lab at R&D. I'm going to develop our master RPM curve for our USB i24. Typically, we send all of our fans for AMCA testing, in which they develop the curve for us. When they test our fans, they do it with no accessories on top of our fans. It's just the fan itself. So as you'll see here, we have no discharge cover, no dampers, no discharge extension anywhere on this unit. We're just testing the fan itself, and we'll go over all of the parts of our test rig next. Here we have our test rig to get our master RPM curve. To my right, we have our fan. To my left, we have our restriction. So as air comes through on the left side, we'll be passing through our reader right here. Here we'll measure our air velocity and convert that to a CFM. We'll measure our static pressure as close as we can to the inlet, and we'll get our brake horsepower reading from our VFD inside the fan all the way to my right. So here we see our test rig. We have this long piece of duct attached to our inlet here, and we have 2 points on our duct here. We have a port for total pressure and a port for static pressure. So our short ridge, which is our pressure reader right here, can take the difference of our static and total pressure, and that gives us dynamic pressure. Once we have dynamic pressure, we can convert that to a airflow or air velocity in feet per minute. And then once we know that, we can multiply that feet per minute by our area of our ductwork, and that gives us our CFM.
In the previous video, we looked at this difference in dynamic and static pressure and how it can be used to calculate airflow. And this setup does exactly the same, but it has to be much more accurate. For example, air doesn't flow at the same rate within a duct. It actually travels faster through the middle. So rather than picking up one single dynamic pressure point, this setup uses several to account for these differences.
It's actually interesting. It's a grid of pitot tubes inside, because when you do a duct traverse, there's a specific location in duct that you measure airflow relative to the size of the duct and how far away the boundary layers are. So there's a specific grid we use to measure pressure inside the duct, and we bring that out and average that pressure across the entire duct.
Now that we have our CFM at point number 1, we also need our static pressure reading. So here we have a manometer. We can read our static pressure. And once our fan turns on for our test, we'll see a reading at the inlet. You want to get this reading as close as you can to the inlet. Here we have our static pressure probe. So in order to get a proper static pressure reading, you want to insert this probe opposite of airflow. So we know we have our exhaust fan with air flowing through the duct into the inlet out discharge here. Airflow is coming this way. You want to make sure our probe is opposing airflow in order to get a proper static pressure reading.
To produce a complete and accurate master RPM curve, we need to gather data at a range of static pressures. From zero static pressure, or basically no restriction, to a small enough restriction that air actually stops flowing through the system altogether. And to control all this while maintaining the most laminar airflow, we use something called a variable iris.
Here we have our iris. So we have 10 points set up on our iris, designated by these 10 points marked in marker right here. So as we close this iris, we're going to increase the resistance and restriction on the airflow. So we need 10 separate points to get a really accurate fan curve. We're going to close this iris step by step, and that'll build our fan curve. So at each point, we need our CFM, our static pressure, and our brake horsepower. So we've covered CFM, we've covered static pressure. Now we need the brake horsepower at each point during our test. We can grab that from our VFD. So during our test, we can come in and come to a certain parameter on our VFD, in this case P510. So take that reading, combine that with our CFM, static pressure, and there we have all of our data for 1 point during our test. Keep in mind, this test is all done at a single RPM. We're going to run this drive at 45 Hertz. 45 out of 60 is about 75%. 75% of our nameplate RPM, 1175, gets us about 880 RPM. The entirety of our test will be run at 880 RPM today.
Now it's time to start gathering data for each restriction setting, starting with an open restriction and virtually zero static pressure. For each setting, we'll record the static pressure, calculate CFM based on the dynamic pressure reading from the duct traverse, as well as brake horsepower based on the kilowatt reading from the VFD.
0.1721.
For each data point, the engineers will record several readings,
0.1677.
and then average them out to improve accuracy.
0.1682.
Okay.
So once all parameters are recorded for this setting, John here will close the restriction by 1 step, which will increase static pressure while also affecting airflow and brake horsepower.
We're getting a reading of 1.1.
Then rinse and repeat until all 10 iris settings are accounted for.
1270. 1.22. 1.89.
Hit stop on the VFD.
Yep.
Okay, so we've got our test data, which was gathered at a constant speed of 880 RPM. Let's develop this into a full fan performance curve. First, we're going to plot each point, looking at static pressure on the y-axis and resulting airflow on the x-axis. And if we connect the dots, we get a sort of curve. And so this is what we call our master RPM curve, which will tell us the relationship between airflow and external static pressure at one set RPM. Now, there's another way to express this relationship using something we call a K-factor or system constant, the equation for which looks like this. So let's pick one of our test data points and plug in the numbers. In this case, our K-factor is 3.76 times 10 to the negative 7. So now that we've used real test data to find this K-factor, we can turn the equation around and use this constant to relate airflow and static pressure at different fan speeds, as long as the system design stays exactly the same. So say we keep the same restriction on our fan, but speed up the fan to reach a flow of 2500 CFM. The K-factor equation will tell us how much static pressure will actually build up then, and we can plot this new point. You can see that since we're moving more air, we're also generating more static pressure at this new point. And we don't have to stop there. We could in theory plot every possible point in the system, giving us what's called a system curve. And once that's done, you don't have to do any of the math anymore. The relationship is simply visualized. Interestingly though, this curve is only useful for this particular configuration. If you do the math for these other data points, each one will have its own unique K-factor. And that's because we fundamentally change how the fan and duct system works every time we change this restriction. In other words, every time we change the system design, we get not just a different amount of airflow and static pressure, but a mathematically different relationship between the two.
So what that means is if you change anything in the system, static pressure wise, so if you open up a duct, access door, or a damper placement changes, or you even change the design of the duct itself, anytime you do that, you're adjusting your CFM and static pressure point, which is jumping you from one K-factor to another K-factor.
Now that we've learned about K-factor, we can start plotting our RPM and horsepower lines. And to do this, we'll have to use the fan affinity loss. We learned about these in the last video, but in summary,
there are three basic sets of fan affinity laws, and it relates fan RPM to CFM, fan RPM to static pressure, and fan RPM to fan power.
let's use the first fan law to plot another RPM line. Say we wanted to plot 1200 RPM. We'll start by using the same data point as before. All we need to do is plug in the known RPM and CFM values for this point, and 1200 RPM for what will be point 2. Then we solve for CFM2, and we get 2900 CFM. Since we already have our K-factor in the system curve drawn, we know how much static pressure will build up in this system with this amount of airflow, so we can just plot that point. And if we perform the same calculation for every system point, we can draw out this 1200 RPM curve and easily do so for other speeds. I say easily because in reality, you would use software to do this for you. Here's a peek at the spreadsheets Josh developed to create some of these curves. Now, this graph is already very useful as it is, but it's missing something pretty crucial, and that is horsepower. It was a Scottish guy named James Watt who first defined horsepower when he determined that an average horse could lift a 550-pound weight by 1 foot in 1 second continuously during an 8-hour shift. Multiplied by 60 seconds, this comes out to 33,000 foot-pounds per minute. So we have units of force, distance, and time. Force and distance together equals work. And work over time, or the rate at which work is done, equals power. These same variables can be converted to this equation, which is a bit more useful with spinning objects like fans. Watt seemed to be all about power, and he also defined wattage as a unit of power, where 1 horsepower equals 746-ish watts. This all happened before electric motors were even invented, when steam engines were starting to replace horses.
Horsepower eventually became a worldwide term of how do you measure power of a motor. Is it a 5 horsepower motor or a 10 horsepower motor? That is the maximum amount of power that the motor can generate. It's the nameplate power, say 10 horsepower. So what is brake horsepower? Brake horsepower is the actual amount of power that the motor is utilizing at any given time. So just because you have a 10 horsepower motor doesn't mean you're using 10 horsepower. Motors are commonly used under their max output power, and that's called your brake horsepower. A 10 horsepower motor may only be using 6 brake horsepower at any given time. And with modern VFDs, we can monitor how much power that motor is utilizing at any given time and present it in brake horsepower or kilowatts.
To finally plot brake horsepower in this curve, we'll be using fan law number 3, which relates horsepower to either CFM or RPM. In this case, let's use CFM. So for example, we know from our test data that at 2,119 CFM, the fan was using 1.45 brake horsepower. So let's say I wanted to know where the constant 2 horsepower line lies in this graph. I would plug in 2 horsepower, and the resulting airflow after the calculation is 2,359 CFM. Just like last time, we can relate this airflow to static pressure by using the system curve and plotting that intersection. And if we repeat for each system curve, we've got our complete 2 horsepower line. Then using software, we can quickly add whatever horsepower lines we want. And that's it. That's how we build a full fan performance curve. Now, I know it's not very likely that you have to know how to build your own performance curve from scratch, but I do feel like going through this example helps take some of the mystery out of it. And now that we've made one, let's start using performance curves to understand how to size fans and motors for different applications.
All these fan curves are basically used to size up the fan. So there's a couple things that you're doing when you're looking at these fan curves. You're looking at the fan performance. Each fan curve is very specific, so it's looking at each fan unit itself, and it also looks at the fan wheel, and it also looks at the fan motor. So you're basically sizing up each fan based on the fan curve and making a selection for your fan unit that you want, which motor that you want in that fan itself. When somebody asks me what fan do you want to select, I'm always looking at, are you doing exhaust or are you doing supply? So that's kind of how we start everything out in NOLA. And if you're doing something that you want to exhaust air out, then we start looking at, okay, what's the application? Is it general application where you're just pushing air out of the wall of a building? You can use a centrifugal fan if you want to, you can use a prop fan. Once you start getting into grease applications, now we're looking at centrifugal wheels or mixed flow wheels only. The temperature also is a big factor, and one of the reasons that we don't use prop fans for grease applications. Static pressure is one thing, but also as you start to increase your temperature, the wheel itself has to be made out of certain metals and be structural. When you weld together our centrifugal or mixed flow wheels, they're very strong, so they can handle very high RPMs. And then once you start to bring temperatures into it, you have to make sure that the wheel can sustain those RPMs without failing.
Let's say we have a commercial kitchen hood which requires 2000 CFM of air exhausted at a static pressure of 1 inch. It's not a particularly heavy grease application, so to match we decide to use a direct drive upblast fan. But how big of a fan should we pick?
I've got 2000 CFM at 1 inch of static. I'm looking at centrifugal upblast fans again, and I get a couple different selections available through NOLA. The first being a DU85. So that DU85 is a 15-inch diameter centrifugal wheel, and we're running at 1,434 RPM. I would say we're in the middle of the curve, but we're on like the upper middle of the curve. It's still a pretty good selection, but if we compare that to a DU180, we're looking at only 997 RPM, and we're now down on like the lower 1/3 of the curve. So same CFM, same static pressure, but you can see here the differences between where you are in the curve compared to the maximum RPM, minimum RPM. And then to take that even further, we can go to a DU200, which is a 20-inch wheel, and now we're pretty far on the left side of that curve. So in my opinion, you'd probably be oversized on a DU200 here just because we're pretty far on the left side. It's pretty oversized. It's only 924 RPM. So we're not that much slower than the DU180, but that DU180 kind of puts you right in the middle of where you want to be. Gives you plenty of lead room for any changes. You're probably going to be pretty good on noise as well, and then your RPM and horsepower are also very efficient. We've got some different shaded areas. So we've got this entire area here, which is yellow. I like to refer to that area as kind of like the warning track, like in baseball. We allow people to select in that range, but we don't recommend going into that range or above that range, just because once you start getting to that range, you're very, very close to the maximum output that fan can perform. So it doesn't really leave you with much adjustment in the field.
These yellow and red shaded areas will appear automatically in our software, and they'll adjust dynamically based on a few factors. These factors can be split into two main categories: fan limitations and motor limitations. Before a motor is even selected, like in this case, we have to consider that the fan is designed to house up to a certain size motor. In this example, the limit is 3 horsepower. So the red shaded area represents anything that would require more than 3 horsepower. We can't go there. The other fan limitation is maximum RPM. Say hypothetically that this fan could only handle 1500 RPM. The red shaded area would hug that line.
We've done extensive testing here, and based on feedback from the field on the max RPM that our wheels can go to. We have max RPMs of what we want them to be when they're in each particular fan. We also look at the max RPM that you can actually attain based on the motor that you have selected.
And now we're getting into motor limitations. So let's review motors for a bit. For the vast majority of applications, you'll be selecting either a 4-pole, 6-pole, or 8-pole motor. A 4-pole will have a synchronous speed of 1800 RPM. This is the speed at which the magnetic field rotates, so to speak, at 60 Hz, which is what we would consider full speed. As we increase the number of poles, the speed of the motor will decrease to 1200 RPMs for a 6-pole and 900 RPMs for an 8-pole. And I should mention that these are the speeds the motors will attain without any load. As soon as we attach something like a fan wheel, there will be some slip between the rotor and the magnetic field induced by the stator, and we usually estimate the slip to be about 50 RPM. That's why motor nameplate speeds are a bit lower, since nameplate speed is considered to be at full load. Now, when we pair these motors up to a variable frequency drive, we can reduce the frequency and change the speed. But we have to remember, as the speed comes down, so does the horsepower output. So for example, if we take a 2 horsepower, 1800 RPM motor and run it at half the speed, it will only output 1 horsepower maximum. It's a nice linear relationship, in theory at least, but one we have to pay attention to. Let me show you this 2 horsepower, 1740 RPM motor within this fan curve. The red shaded area has moved down now, and it seems to be following an RPM curve just under 1300 RPM. And you might say, shouldn't the limitation be 1740 RPM or 2 horsepower? It's neither of those. And that's because, well, we don't have enough horsepower to even get to 1740 RPM. You can see that would take over 3 horsepower, we only have 2. But we also can't even get to 2 horsepower. And I know that seems weird, but it's all in the relationship between speed and horsepower. Our software actually calculated the limit here is 1283 RPM, so the maximum frequency out of the drive should be 44.2 Hz. How do we get this number? Remember, horsepower is determined by torque and speed, and the fan laws assume that this torque will remain constant even at lower RPMs. But in reality, torque does not remain linear with speed, and this relationship varies from motor to motor, even from manufacturer to manufacturer. But there is something we can do to maximize torque at different speeds, and that is to correctly set up the VFD to optimize for the target speed. We can tell the VFD at what frequency to deliver the maximum rated voltage to the motor, basically aligning the max output of the motor to the necessary power requirement of the fan. The way the drive achieves this is by varying the voltage per hertz. This results in an energy output that is not solely determined by speed. And doing this has many benefits. It allows us to often expand the range of operation of the motor-fan combination due to increased torque at lower speeds. It also keeps motor slip down, which actually reduces current draw at these speeds. In the end, this 1283 RPM or 44.2 Hz number is calculated based on what we can achieve in practice with this fan, the selected motor, in a properly tuned VFD. So then, what happens if I try to run this motor at, say, 60 Hz? Nothing good, really. We're already at the limit of torque, right? So we're just going to get more and more slip. This also means more and more current draw, and if we don't have a current limiting device, that means we're going to burn up this motor rather quickly. Take a look at what happens if we also pick a 2 horsepower motor, but instead of it being a 4-pole, it's a 6-pole motor, with a nameplate speed of 1150 RPM. Funny enough, even though this motor is designed for lower speed, in this configuration we can run the fan even faster than with a 4-pole motor. And there's a couple reasons for this. The first is that we're just using more of the available horsepower of the motor because of the 6-pole design. At 1150 RPM, we have the full 2 horsepower, whereas before we only had a fraction of that. But also, we're able to overspeed this motor past 60 Hz, up to 74 Hz. Most induction motors driven by a VFD do have a higher RPM limit than what is achieved at the nameplate 60 Hz. Usually these motors are rated all the way up to 80 Hz as long as current draw stays within limits. In this case, the limit is 74 Hz. And in this configuration, this is very useful, since we expanded our available range just due to this overspeed. Now let's get back to the example of 2000 CFM at 1 inch of static. We can go ahead and plot that in the curve. And we see that, okay, with this motor selection, we have a ton of headroom here. What I mean by that is, say this was specified for new construction, right? And in the field, once everything is installed, we end up for whatever reason with 1.5 inches of static instead. We have plenty of margin to speed up the fan and still meet the 2000 CFM requirement. But how much margin is too much margin? And does it matter? One way we look at how much buffer a motor has is by calculating the percent load. Percent load is how much brake horsepower is needed of the motor over how much horsepower it can produce at that speed. So if we go back to 2000 CFM and 1 inch of static, the fan required 0.692 brake horsepower, while at that speed, this specific motor could produce 1.73 horsepower. So in this case, the percent load is only 40%. And for most applications, we try to get this number closer to 70% or at least above 50%. And the reason for that is motor efficiency. Unfortunately, as much as we'd like to, we can never convert 100% of the energy going into the motor into useful work. There's always some waste in the shape of noise, heat, vibration, and we call this waste losses. Efficiency is basically the ratio of energy put to useful work over the total energy drawn by the motor. When it comes to motor selection and pairing with the fan, there are two major factors that influence efficiency: percent load and percent speed. As we just mentioned, we try to keep the percent load around 70%. We also try to keep the motor speed at a minimum of 50% or 30 Hz nameplate speed, especially with induction motors. And here's why.
So for EC motors, because that motor is coupled with that drive, the efficiency is very high to start, and as you turn the RPM down for those motors, the efficiency stays very linear for the most part. It doesn't drop off as fast as an AC induction motor. AC induction motors, we use premium efficiency motors, so you're looking at 90 to over 90% efficient motors, but a lot of those motors have a peak efficiency to them, and as you turn them down too far, you start to run into issues with efficiency dropping off if you look at the actual efficiency curves. It's another reason that we limit our min RPM, because when you start to reduce the speed too far down, if you have a motor that's designed for 1750 RPM and it's only running at 25%, so 15 Hertz, it's gonna have a lot less efficiency down there, which can hurt you and use quite a bit more energy as well.
So why does this happen? Why are motors more efficient when utilized at higher speeds and loads? Consider this: if we take the fan wheel off the motor and run the motor at 60 Hz but 0% load, then all of the energy going into the motor is used to excite the windings of the motor and overcome the mechanical losses of friction in the bearings. This may only take, say, 50 watts, but 100% of that wattage is considered a loss because zero useful work is being done by the motor. So in this scenario, the motor is 0% efficient. Now imagine we put a very undersized wheel in the motor, bringing the total energy draw to 150 watts. 60 of these watts are still going into the motor just to excite the windings and overcome bearing friction, a bit higher than before since now we have a load. And 90 watts are going into actually producing useful work by spinning the fan. If we do the math in this scenario, the motor is now 60% efficient. So finally, let's put a correct sized wheel in the motor. Now the motor is drawing a total of 780 watts. 80 of these watts are motor losses, and 700 watts are converted to useful work by spinning the wheel. So in this scenario, the motor is running at nearly 90% efficiency. This efficiency will peak somewhere between 50 and 100% load, usually around 75%. After that, there may start to be proportionally higher motor losses, which will cause the efficiency ratio to decrease slightly. So this all shows how efficiency is dependent on percent load. But what about speed? Let's take the last scenario and bring the speed down to 30 Hz, or half speed. Remember from the fan loss that the power required by the fan will not decrease linearly like the available power from the motor. So let's go ahead and put a bigger fan wheel on and maximize our percent loading to take that out of the equation. At 30 Hz, we now have half the available power output to the fan. But as you can see, the motor losses actually stayed fairly constant. They did decrease a bit, but proportionally not as much as the motor output. That means the more we slow down the motor, the less efficient it becomes, as these two lines start to converge. Furthermore, we don't like to slow motors too much because then we also start to lose some of the cooling across the stator coils. Inverter duty motors are better equipped to handle these lower speeds, but by setting limits on both the minimum speed and the percent load on the motor, we ensure that we use that motor within or pretty close to its peak efficiency and with appropriate cooling. So in our example we keep coming back to, we were at 52 Hz, which was okay, but the percent load was 40%. So let's stay with the 6-pole motor, but this time select the 1.5 horsepower option. If we do the math, the percent load is now 53%. We could even go down to a 1 horsepower motor and it would be at 80% load. But now we're pretty close to the edge. This may still be an okay selection, it would be pretty efficient, but remember, if anything changes in the field, you may just not have enough horsepower to do much about it. Clearly, there are many factors that go into a fan's overall efficiency. And so far, we've only been looking at the motor. This is why AMCA has developed a high-level approach to putting all these factors together with something we call FEI.
FEI is Fan Energy Index, and basically it's what is deemed to be an acceptable efficiency or energy use. It's basically wired to air, so it's looking at all of your input for your electrical load, and it's comparing that to how much air you're moving at each static pressure, and it's deeming it either acceptable, meaning that it's better than the efficiency that they expect, or not acceptable.
FEI will end up being the ratio of how much energy our system uses at a given airflow and static pressure versus an established baseline number at the same airflow and static pressure. So in order to know this number and correctly plot it in our charts, we have to account for a bunch of factors, because in the end we have to know just how much power the fan and motor combination will draw under all possible conditions.
We look at things such as the efficiency of the motor, whether or not there's a use of a VFD, if it's direct drive or not direct drive. We also look at the fan types, and there's a lot that goes into that. And basically what that does is we draw this purple line here, and that purple line, as you see, is an FEI of 1. So anything inside of that curve, inside of that bubble, is basically greater than an FEI of 1, which means that as far as the standards go for certain requirements for jurisdictions and states, that would be acceptable. If you selected an area in the curve that was outside of that FEI of 1, meaning that it would be less than 1, then that means that you're not meeting those minimum efficiency standards. So it wouldn't be an approved selection, basically.
So going back to the example of our 18-inch upblast fan, you can see that at 2000 CFM and 1 inch of static, we're right in the middle of our FEI curve. And that's good. Our FEI is 1.294, so we're doing quite a bit better than the baseline requirement. Now, say our design changed and we now require 3500 CFM at 1 inch of static. Our fan and motor can still handle that, barely, but we have zero margin left here, and we're now outside the FEI curve, so our FEI is below 1 at 0.994, so this would definitely not be a great selection. Even if I change the motor to a 2 horsepower motor, we now have a bit of margin, but look, the FEI is still really low. It's actually still the same. Notice also that the actual FEI curve changed slightly when the motor selection changed, and this is based on exactly how each motor performs with this fan. So what we would do here is size up to the next size fan. In fact, to make this more obvious, let's go 2 sizes bigger to a 24-inch fan. Even with the exact same 2 horsepower motor, our FEI is higher, which means we're using less energy than with the smaller fan and motor. Of course, we'd probably want to give ourselves a bit more margin, but even with a 3 horsepower motor, our FEI stays quite high. And how can this be? Well, it actually takes less brake horsepower to turn this bigger wheel slowly than it does to turn the smaller wheel faster. Mostly because we're asking the air to move much faster with a smaller wheel than it does with the larger wheel. And as we learned in the last video, higher airspeeds are generally less efficient.
In general, you kind of want to select the largest fan wheel that you can, given the motor combinations, and there's a lot of other things that go into it, like the weight of the fan, the space of the fan that you can use, the CFM and things like that. But running a larger fan wheel at a slower speed is usually much better and more efficient than running a smaller fan wheel, the same CFM, same static pressure at a much higher speed. Running that larger fan wheel at that slower speed also generally has less static pressure involved because there's bigger ducts, less noise, things like that. So there's other benefits to it, but you don't necessarily want to be selecting anything down here because now you're bottoming out on that range and you can't slow the fan down if you oversized it. You don't want to be running up in this area because if you have any selections that you're right on that edge, maybe there's slightly smaller ducts or a 90 in the ductwork, some ductwork change that you didn't expect. Your static pressure might be slightly higher than you expected. So now you bump up and you basically don't have enough horsepower output from your fan.
Another way to get caught off guard is to forget to include air density in your calculations. The higher the temperature, the lower the air density, and the same goes for altitude. So when you take a breath in Denver, your lungs are bringing in the same volume of air as at sea level, but since the air is less dense, there's less mass of air within that volume, and that's why you get less oxygen. This all seems simple enough, but when it comes to fans, things get a little bit more complicated. See, fans are also constant volume machines, so for every revolution of that wheel at a higher elevation, it should move the same volume of air. But it doesn't, or at least a scenario where this happens is highly unlikely. Say we have a fan connected to this duct system, and at sea level we're moving 2000 CFM at 1 inch of static, spinning at 1000 RPM and consuming 1 brake horsepower. Okay, now if we take this setup and put it on top of a mountain at 10,000 feet, what will happen? Let's say we set the fan up so that we're moving 2000 CFM again. How much static pressure will be developed? Since the air is less dense and we move the same volume of it, there will be less static pressure developed in the system. If you think about it, this exact system will never be able to develop that exact combination of 2000 CFM and 1 inch of static at altitude. Just like you will never be able to get the same amount of oxygen with one breath at that altitude. This means our K factor will be different, which means the fan is no longer going to spin at 1000 RPM to move that same 2000 CFM. It's also not going to use 1 brake horsepower. So what will these numbers be? Without being too specific, the fan will actually spin slower and consume less power up here than it did at sea level, while moving the same volume of air, but moving less mass and thus developing less static pressure. Okay, if you've ever looked at this topic before, that example might seem kind of confusing and maybe even a bit backwards. And I'll be the first to admit that this is a very confusing, kind of mind-bending topic. And I think one reason why is that the way this is usually presented only considers fan performance. Let's look at an example so you can see what I mean. We've been looking at this upblast fan for a while now, at 0 feet elevation and with an air temperature of 120 degrees, which accounts for the heat of cooking appliances. Let's put that side by side with the same fan moving the same amount of air at the same static pressure, the same temperature, but at an elevation of 10,000 feet. Our software automatically calculated that the fan at 10,000 feet is having to spin faster, and because of that, it's using more brake horsepower. But wait, that's the opposite of what we just said in our last example. So what gives? The difference is that this example is calculating fan performance at the same CFM, but also the same static pressure, which means these two systems cannot possibly be the same. The fans may be the exact same, but the system at elevation has to have some feature that is more restrictive, like a smaller duct section, for example. Otherwise, it could never achieve the exact ratio of 2000 CFM and 1 inch of static at 10,000 feet. And once you understand that none of these comparisons are truly apples to apples, some things start to make more sense, like the fact that the fan is spinning faster to achieve the same airflow. And maybe that's still confusing to you, so let's take a look at how these RPM and horsepower numbers are calculated. In this case, the software did it for us, but I'll show you how. Here's a chart that shows the correction factors for different altitudes, but at a constant temperature of 70 degrees. And these numbers simply correspond to the density at sea level when compared to different elevations. For example, the air is 1.45 times denser at 0 feet elevation when compared to 10,000 feet. We use this correction factor to understand how this very same fan and system would perform under equivalent sea level conditions. So what are equivalent sea level conditions? Well, we use the correction to multiply the 1 inch of static at sea level, and we get 1.45 inches of static. If we look at the curves now, the speed of the two fans matches. That's how we calculate that the fan at 10,000 feet has to spin at 1155 RPM. Again, at the same speed, the fan at elevation is going to develop less static pressure because the air density is lower. Also, since the air is less dense, this fan is going to do less work. So we can divide the horsepower at sea level by the correction factor, and that gives us our resulting horsepower at 10,000 feet. Okay, so we had a scenario where at elevation we just worried about airflow, and the fan could spin slower and at a lower brake horsepower. And then we had a scenario where airflow and static pressure matched at elevation, and the fan had to spin faster and at a higher brake horsepower. And this is why details matter. When looking at these calculations, we have to understand whether those static pressure specs were given at sea level or at the right elevation, because that changes everything. The same goes for temperature. do we have the correct temperature that the fan is going to see? It matters. And things can get even more complicated when we're talking about heating and cooling.
When the airflow has a different density, heat transfer is different as well. So we also take that into account when we're looking at the performance of our cooling coils or also the performance of our furnaces. You're looking at winter design temps, you're looking at summer design temps, and then we even go as far as looking at microclimates. So all of our altitudes and ambient temperatures are based on your ship to zip code. But if you're living in a zip code that might have a mountain in it or something like that, you have to adjust that to make your density as accurate as possible.
System Effect tries to explain the difference between a theoretical fan curve and what's actually occurring in operation. So for example, on a theoretical fan curve, these curves are developed with very laminar flow going in and out of the fan with no dampers or elbows near the fan inlet or discharge. System effect is an impact on the fan due to field conditions. For example, if you put a 90-degree elbow right near the inlet or discharge of the fan, that's a form of system effect. Or if you put turns in a duct very close to one another, where one turn or elbow can affect the second elbow, that's another version of system effect for the duct itself, not only the fan. So you have to be aware of all these system effects and dynamic effects in the field to accurately size fans for the application.
Let's take a centrifugal fan in free air. System effect is typically most apparent on the inlet side. So we'll first study what's going on here without any ductwork attached. The air that's drawn towards the fan here comes from all directions around the duct. And since it enters the inlet plenum and wheel right away, there's not enough room or time for all these airflows to even out, and a lot of turbulence and swirl are happening in this area. Adding a straight length of duct before the inlet would still create that turbulence where the duct starts, but the air now has enough time to diffuse and become more laminar before it reaches the fan. For this reason, EMCA recommends a straight run of duct at least 3 duct diameters in length before a fan inlet. So let's say that we're moving 1000 CFM with this configuration, but now we need to make a 90-degree turn in the duct. The ideal solution would be using a completely smooth sweeping radius elbow. And here we have a mitered one, which is more likely what you'll find with round ductwork. In this case, we will still see an airflow loss, but only about 3%, which is acceptable. If we didn't have this much room though, we could place the elbow closer or even right into the inlet, but the losses would be greater because the air entering the fan would not be uniform, which means the wheel itself would be loaded unevenly. This is never ideal and results in some inefficiency, thus the airflow here being lower. So in any scenario where we don't have 3 duct diameters before the inlet, it's helpful to add turning vanes in the elbow, which help maintain a more even airflow into the fan and minimize system effect. Now, a traditional inlet box going right into the fan would be worst case scenario here, with this extremely swirly, turbulent air loading the wheel so unevenly that we see up to a 23% reduction in airflow. Even when we move this inlet box 3 duct diameters away, we could still see a pretty large airflow drop. So there are scenarios like this one where a 5 duct diameter spacing is recommended. But then the question is, if you have this much room, why use a square inlet box in the first place? Cost savings, maybe? Remember though, if you have to speed up the fan to make up for system effect, the fan laws tell us that for a 10% increase in speed, the fan will consume 33% more power. So is that worth it? Almost always the answer is no. The inlet and outlet of the fan are just not places to cut corners. And yes, the outlet matters too. The air leaving a centrifugal swirl has a very uneven velocity profile. So it's important to give this air time to diffuse and even out before encountering a fitting or elbow. The distance at which this is achieved is called 100% effective duct length. EMCA states that at most airspeeds we're dealing with, this happens at about 2.5 duct diameters from the fan outlet. So if we place an elbow right after that, yes, we'll still see a reduction in airflow. But at that point, that's just part of the static pressure buildup in the system. However, if we place that elbow before the airflow is fully developed, this elbow is actually going to start affecting how our fan is operating in a more direct way. The swirl created by the air having to take a turn so close to the fan can hurt fan performance by up to a 16% drop in airflow. Interestingly, the direction of the elbow relative to the rotation of the wheel matters here, where in this configuration it only drops 8%. The radius of the elbow is also important. The smoother the turn, the less of an impact on airflow, but it's still important to maintain the 2.5 duct diameter rule whenever possible.
Elbows or turns being too close to the discharge of a fan will actually cause some structural damage to fans, not only fan performance, but vibration issues. And vibration leads to premature failure of some components in the fan. So it's very important to obey those minimum distances on the inlet and the discharge of a fan. And then as a general rule, you want to make ductwork as large and as straight as possible between the point where the air starts and the fan inlet or the fan discharge and where the air discharges.
With system effect being such a key player, it's always good to give yourself some buffer when sizing up the fan. But in the end, how do we really know exactly how much air that fan is moving when installed in the space? We looked at test and balance in the previous video, which is great because it can account for any leaks in the system. And it was simple enough to perform on a restaurant hood. But when it comes to larger, more complex systems with multiple inlets or outlets, this method can get impractical and we think inaccurate as well. There's just so much margin of error from measuring all these points by hand.
We've taken a little bit different approach recently, and instead of relying on field test and balance, we are measuring airflow within our units and presenting an airflow delivered out of our unit to the end user. We have automated equipment, automated tooling that drills holes in the exact same positions in those inlets every single time. So from those 2 points, we have a pressure drop, and if we have that pressure drop, we can compare it to a theoretical static pressure CFM curve and generate an airflow from that reading. Because we've tested this inlet with our wheel in a chamber, and we know that it's installed the exact same way every single time in our equipment, we know that it's very reliable and very repeatable. So we can tell the user at any given time how much air is coming out of our unit. Especially with new outdoor air requirements and building air quality, if we say that we're bringing in X amount of outdoor air into a building or moving X amount of air or tonnage on an application, it's almost like you're going to the grocery store to buy a bag of chips and you're expecting 12 ounces of chips in this bag of chips or 10 ounces of spaghetti in this box. It's a simple way of looking at it, but if we say we're going to do something, we want to make sure we're doing it.
If you made it this far in the video, I just want to say thank you so much for watching. It means a ton to me as a creator and to us as a company to see so many people really interested in these topics. That's the goal, is to take that knowledge from our engineering team and present it to you in the best way possible. So with that, my name is Herman Tabor, and I hope to see you back really soon.